We are in chapter 6, where we are discussing transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the last session on transformation of stresses and strains. Here we discuss transformation of strain in 3 dimensions, strain rosette, and examples in both 2 dimensions and 3 dimensions. These are the sessions covered in background stress and axial loads, strain, torsion, and bending. Chapter 5 was on shear, and Chapter 6 includes transformation of stresses and strains. This session concludes the discussion on transformation of stresses and strain. Earlier, when considering 3-dimensional analysis of stress, we developed 3 Mohr circles which were related to the principal directions. Thus, the z-axis of the element was aligned with the third principal axis. Then rotation was carried out in the perpendicular plane, that is the xy plane. The corresponding Mohr circle was developed. The direction of the principal strain is the same as principal stress. So here again, we can align the z-axis along the direction of the third principal strain. We can then rotate the element in the xy plane. We can develop the corresponding Mohr circle of strain. We can align the y-axis along the direction of the second principal strain. We can then rotate the element in the xz plane and draw the corresponding Mohr circle of strain. We can align the x direction of the element with the first principal axis. We can then rotate the element in the yz plane and plot the corresponding Mohr circle. So, like the case of stress, we'll get 3 Mohr circles of strain for 3 different planes which are orthogonal to each other. In the case of stress, the sum of the diameter of 2 of the Mohr circle were equal to the third. Similarly, with Mohr circle of strain, the sum of diameter of 2 of the Mohr circle of strain will be equal to the diameter of the third Mohr circle. In the plane stress case, there were no stresses associated with the z-ordinate. Since there are no shear stresses associated with the z direction, the z direction is a principal direction. The principal stress in the z direction is 0. So the plane stress case is a specific form of the general case. In the general case, the stress in the third principal direction will not be 0. Even though normal stress in the third principal direction is 0, normal strain will not be 0 in the third principal direction. Now consider the plane strain case. In the plane strain case, there is no normal strain in the third principal direction. However, there will be stress in the third principal direction. So while 2-dimensional analysis of stress and strain are quite similar, 3-dimensional analysis of stress and strain are not totally aligned. The plane stress case has a principal strain in the third direction, and a plane strain case has a principal stress in the third direction. We'll now consider the plane strain case In the plane stress case, for Mohr circle of strain in turn. Here we'll discuss the plane strain case first. The analysis for Mohr circle of strain for the plane strain case is similar to the analysis of Mohr circle of stress for the plane stress case. For Mohr circle of stress for the three-dimensional case, we dealt with two different types of cases. In one case, the absolute maximum shear stress was given by the maximum out-of-plane shear stress, while in the other case, the absolute maximum shear stress was given by the maximum in-plane shear stress. In the plane strain case, for the Mohr circle of strain in three dimensions, we also have two different types. This is the first type, where the Mohr circle of strain is either on the left or the right of the shear strain axis. In the second type, the Mohr circle of strain crosses the shear strain axis. For the plane strain case, epsilon z is equal to epsilon 3 is equal to 0. So for this case, the arrangement of the three Mohr circles will be as shown in figure B1. The absolute maximum shear strain is given by the maximum out-of-plane shear strain. For this case, the arrangement of the Mohr circle will be as shown in figure B2. For this case, the maximum in-plane shear strain gives the absolute maximum shear strain. Here we discuss the plane stress case. The treatment of transformation of strain in three dimensions is not analogous to the treatment of transformation of stress in three dimensions for the plane stress case. This is because for this case, the third principal strain is not zero, while the third principal stress is zero. We can use the generalized Hooke's law to find out the third principal strain. Since sigma 3 is 0, we get epsilon 1 in terms of sigma 1 and nu sigma 2, and epsilon 2 in terms of sigma 2 and nu sigma 1, while we get epsilon 3 in terms of nu sigma 1 and nu sigma 2. So sigma 1 plus sigma 2 can be given in terms of epsilon 3. We add equation 1 and equation 2. Then epsilon 1 plus epsilon 2 is given in terms of sigma 1 plus sigma 2. Earlier we obtained a relation of sigma 1 plus sigma 2 in terms of epsilon 3. So we substitute that relation to get a relation between epsilon 1 plus epsilon 2 and epsilon 3. So using this relation, we can obtain the third principal strain. For the plane stress case as well, the maximum in-plane shear strain may not be the maximum overall shear strain. This is the case if epsilon 3 calculated is either less than both epsilon 1 and epsilon 2 or more than both epsilon 1 and epsilon 2. If epsilon 3 is algebraically in between epsilon 2 and epsilon 1, then the maximum in-plane shear strain is also the absolute maximum shear strain. In both these cases, the epsilon 3 is algebraically less than epsilon 1 and epsilon 2. Here all principal strains are positive, and here all principal strains are negative. Here again all the principal strains are positive. So in the plane stress case, unlike the plane strain case, it does not matter whether the Mohr circle crosses the shear strain axis or not. We take an overall look at transformation of strain in 2 and 3 dimensions. We mainly use the Mohr circle of strain. To start with, we look at the 2-dimensional case. Here we have a general case of an element subjected to stresses in 2 dimensions. It will be distorted due to normal stress in x direction, normal stress in y direction, and shear stress. This diagram shows the distorted element. It has been rotated slightly so that the bottom part ED aligns with the x-axis. In this figure, the original element and the distorted element are superimposed. Epsilon x is the normal strain in the x direction, epsilon y the normal strain in the y direction, and gamma xy is the shear strain. Then from epsilon x and gamma xy divided by 2, we plot point A, and from epsilon y gamma xy by 2, we plot point B. With the diameter AB, we can rotate and get the whole Mohr circle of strain. When it comes to 3-dimensional Mohr circle of strain, there are 2 cases, the plane strain case and the plane stress case. The plane strain case is the simpler of the 2. Plane strain means strain in one plane. So the strain in the z direction is 0. That does not mean that the stress in the z direction is 0. So there can be a finite stress in the z direction. We can rotate this element so that the perpendicular to the faces of this element are all aligned with the principal directions. Again here, the strain in the z direction is 0, but generally the stress will have a finite value. This case is similar to the 3-dimensional Mohr circle of stress, the plane stress case. Now for this case, there can be 2 types of Mohr circles. For case A, this Mohr circle is the xy plane Mohr circle. The xy plane Mohr circle of strain is on one side of the shear strain axis. Here it is shown on the right, but it can also be on the left. The absolute maximum shear strain will be the maximum outer plane shear strain for this case. With case B, This is the XY plane Mohr circle of strain. The absolute maximum shear strain is the maximum in-plane shear strain of this case. The Mohr circle of strain, that is the in-plane Mohr circle of strain, crosses the shear strain axis. Now let us look at three-dimensional Mohr circle of strain, the plane stress case. Plane stress means stress in one plane. So sigma z is equal to 0. That does not mean that epsilon z is 0. Here we have rotated the element so that the perpendicular to the surface are all aligned with the principal directions. We can obtain the strain in the z principal direction from the strain in the other two principal directions unknown. Here again there are two cases. In the first case, epsilon 3 or epsilon z is either less than both epsilon 1 and epsilon 2 or more than both epsilon 1 and epsilon 2. Here epsilon 3 is shown less. In such a case, the absolute maximum shear strain is the maximum outer plane shear strain. In the second case, epsilon 3 or epsilon z is in between the values of epsilon 1 and epsilon 2. In such a case, the absolute maximum shear strain is given by the maximum in-plane shear strain. Here we discuss the strain rosette. With the help of the strain rosette, we can give the strain at a given point in a structure. Consider that scribes have been made at A and B. Here a structural component is shown, but it can also be a mechanical component. Let the straight line distance from A to B be L. This is before load has been applied. After load is applied, let the increase in length be delta. Then the normal strain of AB is delta divided by L. In order to know the strain at a given point such as A, we need to know epsilon x, epsilon y, and gamma xy. So we have three unknowns. If we can find out the normal strains of three straight lines emanating from A, such as AB, AC, and AD, we'll be able to find out the strain at A, as we will see shortly. The normal strains may involve increase or decrease in length. The increase or decrease in length can be given by an electrical strain gauge. It has a thin wire attached to a piece of paper. If there's an increase in length, then there will be a decrease in the area of the wire. The resistance of a wire is given as rho L divided by A, where rho is the material resistivity, L is the length, and A is the area. So if the length increases, the area will decrease and R will be higher. If the length decreases, then the area will increase and R will be lower. So with the increase in length, R is higher and the current will be lower. With the decrease in length, R will be lower and the current will be higher. So from the change in electricity flow, we can give the increase or decrease in length. Consider three strain gauges cemented to the member emanating from the point A. The strain gauges are at three different angles. Earlier we saw that the transformation of normal strain is given by this equation. For the three different angles, we can have three different equations. The strains measured for the three different cases can be given as epsilon theta 1, epsilon theta 2, and epsilon theta 3. In these three equations, the epsilon is known and the theta 1, theta 2, and theta 3 are known. There are three unknowns, epsilon x, epsilon y, and gamma xy, which can be found out. This arrangement of strain gauges is known as strain rosette. This is a 45-degree rosette. This is a 60-degree rosette. For the 45-degree case, epsilon 0 is epsilon x, and epsilon 90 is epsilon y. So from the strain gauge readings, we already know two of the unknowns. We do not know gamma xy. For the 45-degree strain gauge, cos square theta is half, sin square theta is half, and sin 2 theta is 1. Substituting, get this equation. With epsilon x and epsilon y known, we can find out gamma xy. For the 60-degree strain rosette, epsilon 0 is equal to epsilon x. So we know one of the unknowns to start with. Consider theta is 60. Then cos square theta is 1/4. Sin square theta is 3 divided by 4. And sin theta cos theta is root 3 divided by 4. So we get this equation. When theta is 120, then sin 120 degrees has the same value, but cos 120 degrees is minus half. So epsilon 120 is given by this equation. If we add these two equations up, then the term with gamma xy cancels out. And since we already know epsilon x, we can find out epsilon y. If we subtract these two equations, then epsilon x and epsilon y cancels out, and we are only left with gamma xy. So gamma xy can be determined. We now consider examples of different types. First, we deal with rotation of an element. These are the normal and the shear strains of the element. So the element gets extended both in the x direction and the y direction, and there's a reduction of the right angle. Often when discussing strains, we do not use the word micron. is considered to be understood. So in this case, we can use the number 200 or 120. In this case, we are required to find out the transformed strains after a 40-degree rotation in the clockwise direction. We find out the strains both using formula and Mohr circle. So these were the formulas that we earlier obtained. Substituting these values and theta is equal to minus 40 degrees, we get epsilon x dash, epsilon y dash, and gamma x dash y dash. We consider theta as minus 40 because clockwise rotation is considered as negative. The same problem has been solved using the Mohr circle. So the coordinates of A are 200 on the x-axis and minus 95 on the y-axis. Minus 95 because first of all we are plotting gamma x y divided by 2, and secondly the sign used in the Mohr circle is negative. This is because AB and CD are rotating in the clockwise direction. For P, the x-coordinate is 120 and the y-coordinate is 95. So we can plot the diameter AB and then form the whole Mohr circle. A 40 degrees clockwise rotation means an 80 degrees clockwise rotation in the Mohr circle. So we reach the point A dash. We can extend A dash O to O B dash. The x coordinate of A dash matches with this value. Y coordinate of A dash needs to be doubled and its sign changed, which gives this value. And the x coordinate of B dash matches this value. A rotated element is shown here. Here again, the element gets extended in the x and y direction, and the right angle has been reduced. Here we discuss an example involving direction and magnitude of the principal strains and the direction and magnitude of maximum and minimum in-plane shear strain. We consider the element with these strains. So there's an increase in dx and dy direction, and there's a decrease in angle from the original right angle. These are the formulas of direction and magnitude of principal strain. Substituting the appropriate values, we get 2 theta dash 1 and 2 theta dash 2. We also get epsilon 1 and epsilon 2. These are the equations of direction and magnitude of the maximum and minimum in-plane shear strain. So substituting appropriate values, we get 2 theta double dash 1 and 2 theta double dash 2. We also get gamma max and gamma minimum. We can solve this problem using Mohr circle. First, we plot point A. The coordinate in the x direction is 220. The coordinate in the y direction is minus 45. So this is minus 45. For P, the coordinate in the x direction is 140. And the coordinate in the y direction is 35. With the points A and B determined, we can draw the whole Mohr circle. In the Mohr circle, if we rotate from OA in the anti-clockwise direction by this angle, then we come to OA dash, which corresponds to the maximum principal strain. So the element has to be rotated by half. So here, this angle is half of this angle. The element in principal directions is shown here. There is no shear strain in the element. This value is epsilon 1 and this value is epsilon 2. The angle and the principal strains are the same as obtained earlier. Now if we rotate OA in the clockwise direction by this angle, then we come to OA double dash. Now OA double dash corresponds to the plane with the minimum shear stress. Here we have rotated the element by half of this angle. The strain of the element is the same in two directions. The angle is reduced from the original right angle. In this figure, this angle is half of this angle. The normal strains are the same, and here there is an increase in angle from the original 90 degrees. The direction and magnitude of the maximum and minimum shear strain obtained from the Mohr circle is same as earlier. Though the Mohr circle has an opposite sign convention compared to the formulas for maximum and minimum shear strain. We now start looking at three-dimensional cases. We first consider the plane strain case. We have taken an element with these strains. We'll be finding out the maximum and minimum shear strain. The absolute maximum and minimum shear strain that we'll find out can both be in plane and out of plane. These are the formulas for the direction and magnitude of the principal strains. Substituting the values given, we find out 2 beta dash 1 and epsilon 1 and epsilon 2. Epsilon 1 and epsilon 2 are both negative. So the in-plane Mohr circle of strain will be on one side of the shear strain axis. As such, the in-plane maximum and minimum shear strain will not be the absolute maximum and minimum shear strain. These formulas are for maximum and minimum shear strain direction and the magnitude of the maximum and minimum shear strain. Substituting these values, we get the direction of the maximum and minimum in plane shear strain and the magnitude gamma 1 and gamma 2 for the maximum and minimum in plane shear strain. We can also obtain these values using Mohr circle. Epsilon x is minus 190. So A is plotted with the x-coordinate as -190 and with comma xy divided by 2 as -125. For B, epsilon is -240 and comma xy by 2 is 125. So we can plot the Mohr circle of strain for the in-plane case. For the plane strain case, epsilon-3 is equal to 0. We can draw the outer plane Mohr circle with half of this value as the center, and the radius is the half of the absolute value of epsilon-2. So this is the outer plane Mohr circle for strain. Maximum and minimum outer plane shear strain will be double of these values. So here we get the maximum outer plane shear strain and the minimum outer plane shear strain. Here we consider a plane stress case. An element with epsilon x, epsilon y and comma xy are given. Also, nu is given. We'll be finding out the absolute maximum or minimum shear strain. This may be in plane or out of plane. Using these formulas, we can find out the direction and the magnitude of epsilon-1 and epsilon-2. So we get these values. Now for this case, epsilon-3 is not 0 generally. We need to find epsilon-3 to understand whether the maximum in-plane shear strain and the minimum in-plane shear strain will be the absolute maximum shear strain. Using formula, we find out the direction and the magnitude of the maximum and minimum in-plane shear strain. Epsilon-3 is given by this formula. With epsilon-1 and epsilon-2 known, we find out epsilon-3. Both epsilon-1 and epsilon-2 are negative, while epsilon-3 is positive. So epsilon-3 is not in between epsilon-1 and epsilon-2. So in this case, the maximum outer plane shear strain and the minimum outer plane shear strain will be the absolute maximum and minimum shear strain. We now look at the Mohr circle. Point A has the x-coordinate as -160 and comma xy by 2 as -105. For point B, epsilon is -270 and gamma xy by 2 is 105. So we can form the in-plane Mohr circle of strain. We have found out epsilon-3, so we can plot epsilon-3. Diameter of this outer plane Mohr circle will be epsilon-3 minus epsilon-2. The center of this Mohr circle will be epsilon-3 minus half of the diameter, which we get as -60.87. With the center known and the diameter known, we can draw this Mohr circle. Absolute maximum positive and negative shear strain is the double of these two values, which is given here. We have a strain rosette with the strain gauges aligned at 45 degrees to each other. We are given epsilon AP, epsilon AC, and epsilon AE. We are required to find out epsilon AD. Nu is given and we consider plane stress. We are also required to find out principal strains and their directions, as well as the absolute maximum and minimum shear strain. Epsilon x dash is given by this formula. We consider the direction of AB as the x direction. So for AB, theta is 0. Epsilon x is epsilon AB, or epsilon x is 500 micron. For AC, theta is 45 degrees. This equation with theta is equal to 45, epsilon x dash becomes epsilon EAC. So substituting values, we get equation 2. Also with this equation, substituting theta is equal to 135, epsilon x dash becomes epsilon AE. With the values in place, we get this third equation. From the simultaneous equations 2 and 3, we get equation 4. Now we have already found out epsilon x, so we get epsilon y. We can substitute the values of epsilon x and epsilon y to get gamma xy. Now with AB as the x direction, AD is the y direction. So epsilon AD is epsilon y is minus 655 micron. We earlier obtained the normal strain and the shear strain at the point A. Using these formulas, we can find out the direction and the magnitude of the principal strain. So we get epsilon 1 and epsilon 2 as shown. Also using these formulas, we can find the direction and the magnitude of the maximum and minimum shear strain. These are the magnitude of the maximum and minimum in-plane shear strain. We next find epsilon 3 using the values of epsilon 1 and epsilon 2 already obtained. The value of epsilon 3 that we get is in between epsilon 1 and epsilon 2. So in this case, the maximum in plane and the minimum in plane shear strain is also the absolute maximum and minimum shear strain. Here the problem has been solved using Mohr circle. At A, the x ordinate is 500 micron. Gamma xy is half of 545. So we get the gamma xy corresponding to A. For the point B, the x ordinate is minus 655 micron. Gamma xy is half of this value. So we can plot AB and form the Mohr circle. If we rotate OA by 26.6 degrees in the clockwise direction, we reach the plane of maximum principal stress. And if we rotate anti-clockwise by 64.73 degrees, then we reach the plane of maximum shear stress, which are the values obtained earlier as well. Here we have a strain rosette with the strain gauges at 75 degrees to each other. We are given epsilon AB, epsilon AC, and epsilon AD. Nu is 0.29 and we consider plane stress. We are required to find out the direction and magnitude of the principal strains and the magnitude of the absolute maximum and minimum shear strain. Let us consider AB as the direction. Then for AB, theta is equal to 0. Epsilon x is equal to epsilon AB. So we have one of the unknowns. Consider theta is equal to 75. So we substitute theta as 75 degrees in this equation. And for epsilon x dash, we substitute epsilon AC. So we get this relation is equation 2. Consider theta is 150. Then we substitute theta as 150 in this equation. And for epsilon x dash, we substitute epsilon AD. So we get this equation, which is equation 3. We use equation 2 and equation 3 as simultaneous equations. Equation 2 is multiplied by 1.73 so that the values of gamma xy are the same in equation 2 and 3, though of opposite sign. We then get a relation of epsilon x and epsilon y. We already know epsilon x, so we can find out epsilon y. Substituting epsilon x and epsilon y in equation 3, we find out gamma xy. These are the values of normal strain and shear strain obtained at A. We use these equations to find the direction and the magnitude of the principal strains. So here we have found the direction and the values of epsilon 1 and epsilon 2. Direction and the magnitude of the maximum and minimum in plane shear strain is given by this formulas. Substituting appropriate values, we get the angle and the value of the maximum and minimum in plane shear strain. Next, we find the value of the third principal strain, epsilon 3, using the values of epsilon 1 and epsilon 2 earlier obtained. The value of epsilon 3 is not in between epsilon 1 and epsilon 2. So the absolute maximum shear strain will not be the maximum in plane shear strain. We develop another outer plane Mohr circle. The diameter of the Mohr circle is epsilon 3 minus epsilon 2. The position of the center of the circle can be found by subtracting half of the diameter from epsilon 3. which we get as minus 336.83. The outer plane Mohr circle gives us the absolute maximum and minimum shear strain, as given here. Here from strain measurement, we find out stresses and forces in a structure. We have taken a rectangular beam of dimensions 200 by 30 millimeter. One end of the beam is fixed and the other end is free. Two forces are acting at the other end. Py is a centroidal force and Px is a vertical force acting downwards. The Young's modulus of the material and Poisson's ratio are given. Strain gauges are attached at point A. Point A is 500 millimeter from the free edge and 50 millimeter from the top. The angle between AB and AC is 60 degrees. AB is parallel to the top edge. Consider a section perpendicular to the centroidal axis of the beam and passing through the point A. Due to Px, the section will be subjected to shear force. Also, due to Px, the section will be subjected to bending. Py would cause an axial force. So the point A will be subjected to sigma y, both due to bending and the axial force. These are the y and the x directions considered. At A, there will be no normal stresses in the x direction. At the point A, there will be shear stresses due to Px. Using generalized Hooke's law, this is the expression of epsilon y. Sigma z is 0 and sigma x here is also 0. So sigma y can be obtained directly, which we get as 200 MPa. Also using this equation, since sigma x is 0, we can obtain epsilon x, which is given as minus nu into epsilon into sigma y divided by E. We use the equation of transformation of normal stress. This angle BAC is 60. So the angle that AC makes with the x direction is 30. So we have 2 theta is 60. Substituting values, we get this equation. We already know epsilon x and epsilon y, so we can find out gamma xy. The Young's modulus is given, so we find G. How is gamma into G? So we can find the shear stress at the point A. The shear stress can also be found out using VQ by IP. Here we have obtained Q of this shaded portion and I of this whole section. Substituting in VQ by IP, we get tau at A in terms of V. We already have the shear stress at A, and equating, we find V or Px, this value. Once we know Px, we can find out the bending stress that it causes at A. The moment is Px into this distance. Using My by I, we get the value of the stress. This stress is due to bending. Subtract this stress from the total sigma y. We get the stress due to axial force at A, which we get as this value. Multiply this stress by the area, we get Py.